now let's take a look at what I call the 68, 95, 99.7 rule. Technically, the more official name for this is the empirical rule. So the way this rule works is if a data set is normally distributed, this is key. This is only applying to normal distributions with mean mu and standard deviation sigma. Then uh, 68% of the data, so 68% of the data falls within one standard deviation of the mean. (95% of the data falls within two standard deviations of the mean. And 99.7% of the data falls within three standard deviations of the mean. So I'm going to quickly give myself a little more space. So essentially what this means is we have our normal curve. Here's our mean. Going out one standard deviation. I'm now going to just count by standard deviations. So here's going up one standard deviation. Here's a second and a third. And then we can do the same going backwards. Minus a standard deviation, minus another standard deviation, and minus another standard deviation. Then what they're saying is 68% of the data falls from here to here, between one hop down and one hop up. So this stretch here is 68% of the data. Then going two hops down from the mean and two hops up from the mean is 95% of the data. And then if we go three hops down from the mean and three hops up, and look at that stretch. That region amounts for 99.7% of the data. So again, if we took the area under the curve from the stretch I highlighted in purple, that would be 0.68 for its area. The stretch I highlighted in blue took that total area, would be 0.95. And the stretch I highlighted in green, that entire area under the curve, would be 0.997. So if we take an example, I have the lengths of newborn female are normally distributed with mean 49.1 centimeters and standard deviation 1.9 centimeters. So some keywords to search for, we do have our normally distributed. Our mean is 49.1 centimeters. So that means mu is 49.1. Our standard deviation is 1.9. So our sigma is 1.9. And then I asked you to draw the diagram. So we're going to put our mean in the center. These are 49.1. So again, this is our mu. Then from here, we should go up by copies of our standard deviation. So we'll go up by 1.9, again, and again. We also should go down by copies of our standard deviation. So we'll subtract 1.9. And if we find each of those values, 49.1 plus 1.9 should be 51.0. Followed by another 1.9 would be 52.9. Followed by one more 1.9 should be 54.8. Going backwards, 49.1 minus 1.9 should be 47.2. Subtract off another 1.9 should be 45.3. And last up should be 43.4. So for each of these, I'm adding 1.9s as I go to the right, subtracting 1.9s as I go to the left. Then what we have is from 47.2 to 51.0. Is 68% of our data falls here. From 45.3 to 52.9 is 95% of the data. And then from 43.4 to 54.8 is 99.7% of the data. So we want to know, what is the probability that a randomly selected newborn female is between 47.2 and 51.0 centimeters? Well, that is precisely our purple region. Goes from 47.2 to 51.0. So that is 68%, or as a probability, 0.68. If we now look between 45.3 and 52.9, that is precisely the blue region that I highlighted. So that is 95% of the data, or a probability 0.95. And then if we look between 43.4 and 54.8, that was that region I highlighted in green, which was 99.7% of the data, or a probability of 0.997. So this is just sort of the basic how we read this. Drawing the diagram, these questions were already essentially answered for me. I just had to look at the diagram to see which region was the corresponding percent. In the next video, we will play around a little more with this, as well as taking advantage of the fact that the normal distributions are symmetric.